This is lecture 12 on permutations in a pure mathematics course on finite group theory at junior and senior level. The first author of the text is Barnard. And here's the text becoming increasingly dog-eared. It's in the Teach Yourself series, and the title is Mathematical Groups. Okay, now those of you who've been following me may notice the new board. Finally, it's arrived, and I noticed some changes in the sense it's, compared to the previous one, the older one, it's 30 centimeters longer. It's 10 which I didn't expect, but it's 10 centimeters shorter. So the proportion, surprisingly, the proportions are such that these board proportions fit the proportions of the image on the camera. So the net effect of all that was that I was able to move the camera a foot closer to this board. So if I seem a little closer to you, that's probably the reason. Also, I don't know what it is, but maybe the chemical treatment of the surface of this board is such that, here, watch. It's just so easy to, I just wipe it off now. I don't have to wash, or I just wipe. So, if only I'd known. Okay, so I now have a bigger board, wider, so that means I can experiment a bit more. And I can put more stuff. I can write a little bigger. I hope you're able to see the writing more easily because it's a little larger. And I can wipe it up more easily. So very nice. So, and this is not so expensive. I can buy 10 of these for the price of a European one, higher quality. In fact, with being able to wipe it so easily may mean that it lasts a long time. So we'll see. Also, another innovation is it's getting hot. It's mid-June almost, 2012. It's getting hot, so I now have, you can't see it, but I now have a fan blowing on me to keep me cool, because previous lecture I was sweating like a pig. So I hope the noise of this fan is not interfering. I hope it's barely perceptible. If not, well, we just keep experimenting. Like, this is the first lecture in the whole series of the deGarisMPC. deGaris, that's my name. So mathematics, physics, and computer theory. So I plan to make hundreds of courses on these three themes, although mostly pure mathematics and math physics, to PhD level over the next decade or more. It's my new career. Right. So this one is this lecture is on permutations. So to permute, I checked in the dictionary just in case my own definition wasn't. I used Wiktionary, Wikipedia dictionary, and they had the same definition. So to permute is basically just to change the order of. Right? So you have something ordered in a certain sequence, and you just change the order. So the verb to do that is to permute, and the noun is permutation. And why are we talking about permutations in this context of finite group theory? Well, you can probably guess. The set of all possible permutations of, say, n, little n, integer, n objects, is in fact a group, but I'm jumping ahead of myself a little. Okay, so firstly, in physical terms, I'll give an example of a permutation, and then I'll translate that, what's going on physically in the real world, if you like, into abstract mathematics. And then from then on, we just forget about the physical world. We're just manipulating symbols. We represent a permutation effectively by numbers, and then play with that representation. And there's a whole branch of mathematics on the group of permutations. Like here's a book in the Graduate Text of Mathematics, the famous mathematical series. If you look at the library of any professional mathematician, they will have many of these yellow and white textbooks. It's a rather famous series in math. And so they're usually just called GTMs, so Graduate Text in Mathematics. And the topic of this one is called the symmetric group, which is in fact the group of permutations. Alright, so let's start with a concrete example. Imagine this here represents a wooden base, right? It's a solid base, and sticking out of it vertically are 3 poles, right? So these are poles, these 3. And imagine I have 2 sets of rings, round rings, and one's red, the other ring is green, and the third one is blue. Okay, and I put one ring on one pole. Forget the upper ones for the moment. So I just have these 3 rings on these 3 poles. One ring per pole. Okay. Now it doesn't matter what the order is, whether it's red, green, blue, green, whatever. So here's one possible ordering, if you like, or configuration. So I put the red here, the green here, and the blue there. Okay. Now I have a second set of rings, 3 rings, also red, green, blue, and I shuffle them, and just by chance, the second ring on this pole, it happens to be green, and the second ring on this pole happens to be blue, and the second ring on this pole happens to be red. Okay, so in a sense, I have a new ordering. This is the old ordering, and this is the new ordering. Okay, so the old ordering would be red, green, blue, and the new ordering would be green, blue, red. Now, the actual poles are irrelevant. Like, if I were to get a saw and cut this block of wood here, the base, here, and here, and just rearrange the order of the poles, I would not change the permutation. Meaning what? Well, the ordering is red went to green, and green went to blue, and blue went to red. But the order that I give you these 3 mappings, if you like, these 3 pairs, like here's a pair, red to green, that's one pair. Green to blue, another pair. Blue to red, another pair. Those 3 pairs, you can put the pairs, these 3 pairs, in any order. That doesn't matter. What's important is the pairing this way. So red to green, green to brown. Sorry, blue to red. Okay, so here's your old order: red, green, blue, and here's your new one: green, blue, red. Okay, that reordering, going from this to this, is called a permutation. Right? And you can see there's 6 possible permutations, right, with 3 objects. Right? Now, very quickly, we forget about letters and names. We just use numbers, because it's a math course, right? So instead of talking about red, green, blue, we can just talk numbers. And so you could imagine these rings. They could all be white. But each ring has a number burned onto it, right? So the ring has an ID, an identifier by its number. Okay? So you could put rings here instead of coloured. You could have like ring 1, ring 2, ring 3, and then you look at the ring numbers on the upper ring, the new ordering. So and it might be like 2, 3, 1. So instead of using colours now, you're using numbers, right? And remember the ordering of the pairs is irrelevant. Like this permutation is the same as this one. Okay? Why? Because the pairing's the same. 3 to 1, 3 to 1, 1 to 2, 1 to 2, 2 to 3, 2 to 3. Now the ordering of the pairs, like 3, 1, 2, is different from 1, 2, 3. That's irrelevant, okay? The only thing that matters is this way, the pairing, the vertical pairing, if you like. Okay, so that's what a permutation is. It's changing the ordering from this to this. Now, so 1, 2, 3, I can map to 2, 3, 1. 1, 2, 3 to 2, 3, 1. You're familiar with this stuff from earlier lectures. That is a one-to-one mapping. That is a bijection from this set, the set of 1, 2, 3, to itself actually. It's the same set. Okay? So you have a bijection from a set of objects, whatever it is in the abstract, to the same set. So here's your mapping function, f, it's a function, and it's mapping from the set A, these, to itself. So mapping from A to A. Okay? So we can look on a permutation then as a bijection, a one-to-one mapping. One here to one here, one here to one here. It's a one-to-one mapping. So it's a bijection, okay, from a set to itself, from A to A. All right?